Inventor Roy Rosser has invented and applied for a patent on a reciprocating crank. This is a novel device that can be used to more efficiently convert reciprocating motion into rotary motion. The novel reciprocating crank may, for instance, be used to create a bicycle that is 50% more efficient than a conventional rotating crank-powered bicycle. This is a video clip of a proof of concept model of the novel reciprocating crank in action. Before explaining how this reciprocating crankshaft operates, it is instructive to understand how it achieves this 50% increase in efficiency over a conventional rotating crank. To do this, we first need to look at how a rotating crank functions on a conventional bike. At the start of a pedal cycle, the pedal is vertically above the drive shaft, and the rider, pushing vertically downwards, applies no torque at all to the drive shaft. The rider is in what is often referred to as the dead zone. Only as the bicycle's momentum carries the crank round can the rider's vertically downward pedaling begin to be converted into torque to power the drive shaft. As the angle of the rotating crank increases, more torque can be applied, reaching a maximum when the rotating crank is angled at 90 degrees, as shown in this plot of the torque against crank angle. As the pedal cycle continues, the useful torque now decreases until the rider enters the next dead zone. When the rotating crank is angled at 180 degrees, the cyclist can once again no longer apply any useful torque to the drive shaft. As the pedal cycle continues with the left foot, the applied torque follows the same sinusoidal pattern. A graph of the torque applied to the drive shaft versus the angle of rotation of the rotating crank is displayed here, illustrating one complete pedal cycle for a rotating crank. In contrast, at the starting point of a pedal cycle with the novel reciprocating crank, the power pedal is positioned at an effective crank angle of 60 degrees. From this starting position, the cyclist can already convert 90% of their vertically applied pedaling force into rotary torque to power the drive shaft. As the reciprocating crank continues on toward the midpoint of the pedal cycle, the torque that can be applied as useful power to the drive shaft continues to rise slightly, as shown in this plot of torque against crank angle. Going further into the pedal cycle, the torque applied to the drive shaft falls slightly, but it does not go beneath where it started, even at maximum crank travel. So there's always nearly 90% or more of the vertically applied pedal power being converted into useful torque. The left pedal now becomes the power pedal, and the cycle continues. This diagram shows the torque applied to the drive shaft versus crank position for one full pedal cycle of a reciprocating crank-powered bicycle. This image combines everything we have discussed so far and compares the torque that can be applied to the drive shaft during one pedal cycle of a rotating crank and one pedal cycle of a reciprocating crank. The shaded green and the shaded red regions indicate the extra torque made available by the reciprocating crank. For a reciprocating angle of 60 degrees, this can be mathematically calculated to be a 50% increase in torque. There is a small price to pay. Because a reciprocating crank only turns the drive shaft 120 degrees during one pedal cycle, for a rider to pedal with their normal cadence, there needs to be a factor of 3 increase in the gearing. This shows the additional gear required to obtain the additional 3x increase in gearing to match normal cadence. Here is our concept cycle, with the additional gear shown in red and the conventional chainring shown in black. So how does this novel reciprocating crank function? Here is a 3D rendering of a proof of concept version of the reciprocating crank. It is two magnetically sprung overrunning clutches, each attached to a bevel gear. The bevel gears are then linked to each other by one or more linking bevel gears. The magnetically sprung overrunning clutch is a novel device that is the subject of a separate patent application by inventor Roy Rosser. Each overrunning clutch has a number of sprags, shown here in yellow. The sprags are situated between an inner shaped structure, shown here in blue, and an outer driving ring, shown here in pink. The shaped structure is rigidly attached to the drive shaft, while the outer driving ring is attached to the reciprocating crankshafts. The sprags are magnetically sprung from the inner shaped structure via magnets located in the square through holes. When the driving ring is rotated in one direction, the sawtooth inner elements drive the sprags to become wedged between the driving ring and the inner structure, effectively locking the reciprocating crankshafts to the drive shaft. This allows torque or power to be transferred from the crankshaft to the drive shaft. When the driving ring is rotated in the other direction, the sprags are freed up and drawn away from the inner structure by the sawtooth inner elements of the outer driving ring. In this freewheeling state, the drive shaft is free to continue rotating in a direction counter to the direction of rotation of the driving ring. The outer driving ring is also attached to a bevel gear. These bevel gears attached to the two overrunning clutches are then linked to each other by linked bevel gears. These linking bevel gears are held in place on a linking gear platform. The linking bevel gears cause the outer driving rings of the overrunning clutches to rotate in opposite directions. In this way, when torque is being applied via a first crankshaft to the drive shaft via a first locked overrunning clutch, the other overrunning clutch is being counter-rotated and is freewheeling, allowing the other crankshaft to be moved back into position, ready to have power applied to it. The two crankshafts can therefore accept linear reciprocating motion and convert it into rotational motion in a single direction. This is exactly what is needed to power a bicycle. The great advantage of using the reciprocating crank over using the conventional rotary crank is that it is 50% more efficient, a factor that will be greatly appreciated by cyclists. So that is it. Inventor Roy Ross's novel reciprocating crank, a novel invention whose 50% increase in efficiency should make it become standard on many, if not all, the 100 million bicycles sold worldwide each year.